Okay, I need to clean this board, and this is going to be very relevant soon in physics, and we might as well get used to the notation, or at least see it at this point. But we might well use it in a lab 2 days hence. We define, for rotation, we define the position theta on a set of xy coordinate axes to be measured from the positive x-axis in the counterclockwise direction, meaning that angles that are measured in the clockwise direction would be negative. Positive angles measured in the counterclockwise direction. So theta is a function of t. Theta is a position function, but it's an angular position function. For example, you've got a rotating beam. Okay, it's rotating the angle theta between a given point on the beam and the positive x-axis is maybe changing in the positive direction, maybe in the negative direction. In any case, theta is a function of t. So it's like a position function, okay, like a position of an object moving along an incline. It's just completely analogous, but now we're not measuring the position of something moving through space, but an angular position of something that's rotating about some axis. We define omega to be the rate of change of theta with respect to t, meaning that omega is delta theta over, approximately equal to delta theta over delta t. Average value of omega would be delta theta over t, just as the average value of our velocity would be delta x over delta t, or delta s over delta t. Okay, so omega is what we would then call an angular velocity. Change in theta divided by change in t. At any instant, that's approximately equal to some change in theta divided by change in t. Okay. And angular acceleration is the rate of change of omega with respect to t. Just like acceleration is delta v over delta t, we're going to call this delta omega over delta t, omega being the rate of change of theta. So approximate value of alpha is change in omega over change in t. Now, we're going to assume that theta equals 1.2 and omega equals negative 0.1 when t equals 0. Now, actually, theta has units. We're going to measure it in degrees, in radians, because that's the easiest unit of angle to use for the things that we're doing, and we'll see that shortly. Because calculus is easier to do in radians, you don't have constants to worry about, and many other reasons. Arc length is directly related to radius and angle in radians. Arc distance on an arc. Distance on an arc. Okay, so omega is negative 0.1. It might well be 0.1 radians per second at t equals 0. Okay, so we suppress the units, but we use them down here. Okay, now if theta is 1.2 radians and omega is 0.1 radian per second, which is what I just kind of said, we want to find the new values of omega and theta after a millisecond. Well, after a millisecond, well, what changes in a millisecond? First of all, I don't think I've got anything down here about alpha. Yeah, I do. Okay. Well, alpha is negative 300 cosine theta, which would be 300 radians per second times cosine theta. So we've got a way of evaluating alpha. So, to get the new values of theta and omega, well, omega tells us the rate at which theta is changing. So if we multiply omega by delta t, we're going to get our change in theta. And alpha tells us the rate at which omega is changing. So if I multiply alpha by delta t, I'm going to get my change in omega. So if I know omega and alpha, I can find the approximate change in theta and the approximate change in omega in a 1 millisecond time interval. Delta t will be the 1 millisecond. Now, that's not going to give me a perfect result, because as theta changes, which it will during that millisecond, so will alpha. Okay, our acceleration will change a little bit because theta is going to change a little bit. So we're not going to get an exact result, but we're using a very small time increment with these functions. It turns out that we can get a pretty good approximation. Okay, so we got to find delta omega and delta theta. Okay, so make sure I see where we're going, because it's been a while since we did this. Yeah, I'm not sure exactly where we went, but I think we went here. And this applies. Okay, so again, theta is 1.2 radians, omega is negative 0.1 radian per second. So our change in theta will be our negative 0.1 radian per second by 0.001 second, and that's going to be negative 0.0001 radian. Very tiny change in our angular position. So this thing is out here at 1.2 radians, about here, and it changes, but just a little tiny bit. You can't even really see it. But we're only looking at the change in 1 millisecond. So if you took 2 snapshots of this, a millisecond apart, you might not even be able to see that it's moved. If you look closely enough, presumably you could. So your new theta is going to be what? Well, theta is changed by negative 0.001 radians. Your theta was 1.2 radians. It's changed by negative 0.001 radian. It's 1.1999 radian. Now to find delta omega, we need to use alpha and delta t. Well, alpha equals I don't like the way I wrote that, but I'll explain it. Negative 300 times the cosine of 1.2. Now that's really negative 300 radians per second squared times cosine of 1.2 for reasons of be clear. So when we multiply that, we've got to multiply that by the cosine of 1.2. Now that's 1.2 radians. Radian is the default unit of angle, so we don't have to write down radians. If we say cosine of 1.2, we don't mean the cosine of 1.2 degrees. If we want to do the cosine of 1.2 degrees, we'd better make that 1.2 degrees. This is 1.2 radians. No unit written, it's radians. Okay, so cosine of 1.2 multiplied by 300 comes out kind of close to negative 120. Yeah, you can check that out, punch it in your calculator if you want to make a good sketch and make a good estimate. And that really means negative 120 radians per second squared. Okay, so now we come all the way up to here. Alpha then is negative 120 radians per second squared. There is a negative sign there that's been mostly erased. And delta t is, again, our 0.001 second. We're still figuring out what happens, approximately what happens during this first millisecond increment. So delta omega is alpha delta t, 120 radians per second squared times 0.001 seconds, and that comes out negative 0.12 radians per second. Well, that turns out to be a pretty significant change in omega, because omega was negative 0.1 radian per second. The change has been negative 0.12 radians per second, so now we've more than doubled our value of omega. Now, omega is fairly small, but 0.1 radian per second is something you can certainly see. That's like going around a circle in about a minute. Okay, that's something you can see. And now we're going around at a rate that would get us around the circle in about half a minute. Okay, so that's kind of significant. So, what do we know? After this millisecond has passed, theta is this, omega is this. Very tiny change, almost imperceptible, probably imperceptible in theta, but a clear change in omega. So now we're moving faster. So in the next millisecond, we expect theta to change by more because we're moving faster. So we find our delta and omega and delta theta to find our omega and theta after another 0.001 second, and I believe here are the calculations. Okay, we multiply our new 0.22 radian per second, negative 0.22 radian per second velocity, angular velocity, by the millisecond, and we get still a really small number of radians, but it's more than twice the change we had before. And alpha is now still about negative 120 because 1.2 and 1.1999 are almost the same angle, and this is very approximate anyhow. So that's not going to change significantly for a while, and it's not really accurate anyhow. You can easily calculate it accurately. So with this alpha, our delta omega is going to be another negative 0.12 radian per second, and our new omega is now going to be negative 0.34 radians per second. So we can keep iterating this process. To find out what happens over the space of 1 second, I have to do this 1,000 times. Take what we got in the last millisecond, apply it to the new millisecond. And every time there's a little bit of error, because really in this first millisecond, omega changed from 0.1 to 0.22, negative 0.1 to negative 0.22 radians per second, meaning that it really averaged something closer to about negative 0.16 radian per second, which means it moved a little further than this estimate says, and that results in every increment in a little bit of error, and you get some accumulating error in the result. Nevertheless, at 1 millisecond, at least for a short time, you're going to get a pretty good approximation.